Well, we're going to start with Chapter 1. I guess that's a good place to start in Section 1. Those of you that have had Calc 2 here, you would have seen some differential equations. And I'm guessing that if you had Calc 2 at another school, you would have also seen some differential equations. That's typically the place that they're covered, at least to some extent. And so what we'll be going over in Chapter 1 will be a little bit of review of what you would have already seen. In fact, you might have already seen even some of the stuff that we'll get into in Chapter 2. But we'll be going a little faster and a little bit more in depth than what you would normally see in a Calc 2 class. So I do strongly recommend that you work on the homework very regularly. Well, the section that we start with, Section 1, will have a lot of definitions and terminology in it. Very important when you're working differential equations to be very comfortable with the terminology and your notation. So, well, let's first address the elephant in the room. What in the world is even meant by a differential equation? What is a differential equation? Most of you had Calc 2 here, so you have no excuse to not know the answer to that, right?
Equation for a more differentials.
Okay, it's definitely an equation, and it has, well, the term differential is maybe just a little bit misleading because we don't normally use differential notation. Normally it's just simply derivative notation. So we're talking here about equations that have one or more derivatives involving one or more unknown functions of one or more independent variables. How do you like that? And this definition, by the way, you'll find in your text, so I don't know, should I write it all out? I'll write out a few key things. So it's an equation involving one or more derivatives of one or more functions involving one or more independent variables. I'll some examples. So that's an equation. See the derivative there. It's sometimes maybe not always obvious what the unknown functions are, but in this case we're simply looking for a function of the form y equals f of x that satisfies this differential equation. It satisfies this equation. In other words, we're looking for a function whose derivative is x squared. Well, this one's simple enough that you already know what the solution to this one is, right? Give me an example of a function whose derivative is x squared. X cubed over 3, right? So here is a solution. Well, I said give an example of a function that satisfies that. It's not the only example, is it? What else can we do? Add 1, add 2, add any constant, right? So there's what we, in differential equations, will refer to as the general solution. But we'll talk about all those issues in Chapter 1. But just to kind of give you a little bit of a preview of coming attractions, this is what we would call the general solution of this differential equation. It's very easy to come up with in this case. It's a solution in the sense that when you take the derivative of this function, it satisfies that equation. And we'll talk a little bit more about solutions in a moment. They won't always be that easy to come up with. In fact, sometimes they're very hard to come up with, and that's why we're spending a whole semester on the topic of differential equations. We'll be looking at various techniques for finding the solutions of these differential equations. But anyway, just back to our definition. So an equation involving, in this case, only one derivative of one unknown function with one independent variable. So the independent variable, remember, is in this case the x. looks maybe just as simple, but it's actually not. See the difference there? What would we refer to as the independent variable in this case? What's the independent variable? And what's the function variable here?
Function variable is t.
Function variable is x. Independent variable is t. So we're looking for a function of that form which satisfies this equation. So the independent variable is t. The unknown function is x. You can tell that from the way the derivative is written. We're looking for the derivative of a function x with respect to t, and we want that derivative to be equal to x itself. Well, once you've sorted that all out and you understand it in that fashion, this is one where maybe just by inspection you know the answer. We're looking for a function whose derivative is itself. How many functions do you know of like that? I only know of one. What is it? E to the x, or in this case, e to t. Again, we could add an arbitrary constant in there. Well, so we can have just one function, just one independent variable. Let me at least give you one that has a little bit more than the other. Partial derivative, so this is one instance where if you haven't seen calculus of multivariable calculus, you might not have seen this notation before, but this is the partial derivative of z with respect to x. Claiming that that derivative has to be equal to this expression. So we're looking for, in this case, function of two variables, and that again, that you get that context from the fact that we're talking about the partial variable here. So we're talking about a function of two variables, x and y. So the independent variables are x and y. This is still only having one derivative. We can make this much more complicated, I suppose, and throw in something like this. So there you want the sum of the two partials to be equal to that expression. I'm not sure if that's even possible, but anyway, there's a differential equation involving two derivatives, one unknown function, two independent variables, and we could go on and on with all kinds of other examples. Maybe let me give just one more. Let's do that. Two derivatives, first and second derivative. It may be a little harder on this one to tell from the equation exactly what the function of what the independent variable would be. We actually have some latitude what we might use as our independent variable, but certainly the function is represented by y here, right? So we're looking for a function y equals, let's write it as a of x, t, we could use whatever variable we want for the independent variable, since it's not specified there. Now if I were to change this up and put something over here, then we want t, the independent variable. So you pick up on what the function variable and the independent variable are from the context of the equation. Well, I haven't said anything about the solutions of this, which I'm not even sure I could find. We could find the solutions of this, and we'll learn how to do that later in the course. That's going to be a big part of the goal of this course, as I mentioned earlier. But before we can even start talking about solutions, it's important to be able to classify differential equations, to determine what type they are, because the solution technique that you use depends a lot upon the classification, the nature of the differential equation. The solution approach that we use here, well, this was just integration. But that's different than what we would do here, because this is not something we can solve just by integrating on the right, although integration does turn out to be an important technique. This one we would solve using different techniques than we would these two. So we need to know how to classify the type of differential equation that we're dealing with. And there are various ways that classification can be done. One way is by type. And there are two types, general types of differential equations. There's ordinary and partial. An ordinary differential equation is one in which all of the derivatives, well, I should say it this way, the unknown functions have only one independent variable. Whereas partial differential equations have unknown functions with two or more independent variables. So this is the only partial differential equation that I have on the board here. These would all be ordinary differential equations. In this course, outside of this section where you'll have a little bit of experience with some classification, we're not going to be dealing with partials outside of this section. We'll be considering exclusively ordinary differential equations in this course. If you look at the title of the text, oh, I guess it doesn't say. Some texts have the word ordinary in the title. This one doesn't have to. For short, ordinary differential equations are often denoted ODE, and partials, surprise, surprise, PDE. We do offer a PDE course here every other year. I can't remember if it's being offered this coming fall. Is it this fall? So if you're interested in PDEs, and want to learn a little bit more about that, there's a course being offered this fall that you could take. Just a little bit maybe about the notation. When we're dealing with derivatives in particular, we have these various ways in which derivatives are often written. There's this notation, there's the prime notation. Anybody remember what this kind of notation is called? It's named after one of the discoverers of calculus, Leibniz, or Leibniz, depending on how you choose to pronounce it. I think I generally say Leibniz, but I'm not sure if that's right or not. So this is the Leibniz notation. This would be an example of Leibniz notation for partial derivatives, and this is just the prime notation. So you just need to be comfortable working with those different notations for derivatives. I guess dealing with partial derivatives, partial differential equations. This could also be written with the subscript notation. So there's that yet another notation in the case of partial derivatives. Second way of classifying differential equations by their order. The order of a differential equation is simply the order of the highest derivative that appears. This is a first order, ordinary differential equation. So a lot of times we'll combine these. So it's ordinary and it's second order. All right, first order. First order. So not, that power doesn't mean anything as far as the order. Order is only determined by the order of the derivatives. This is a first order derivative. So this is another first order ordinary differential equation. First order partial differential equation. Second order ordinary differential equation. So it's just the order of the derivatives. Might seem fairly simple, and it is, as long as you don't get thrown off by some of the distractions that appear in some of these equations. What's the difference? In terms of order, how would you describe this one? this is the way that second derivatives are denoted using the Leibniz notation. What is this? This is just first order. We're squaring a first derivative. So it's not a second order differential equation, it's a first order differential equation. Happens to be one that would be very difficult to solve, if not possible using analytic techniques. But anyway, I won't get too much into solution techniques yet. Let's see. The general form for, let's say, an nth order ordinary differential equation. It's often written that way. That's assuming that the equation can be expressed in a form where, well, and I guess I can't think it couldn't be. So if everything is brought to the left-hand side here, this equation could also be written, well, either using Leibniz notation or prime notation, like that. So the left-hand side is a function of x and the second derivative of y. Same kind of thing here. So it's just a handy way of talking in general about an nth order differential equation, an ordinary differential equation. Now, if it happens that you can solve the equation for the nth derivative, then we do what's called the normal form. So, for example, in this one, it's already in normal form. The highest order is 2, and it's already written in a form where you've got everything else on the right-hand side. This one, well, we'd have to consider different branches, and so it's not convenient on that one to write it in normal form. Because I consider plus and minus radical, that kind of thing. Third way of classifying is by linearity, the presence or absence of linearity. So is a differential equation linear or is it not? And it goes back to this. If this function, capital F, is linear in y and its derivatives, it doesn't have to be linear in x, then we refer to it as a linear nth order differential equation. Linear nth order ordinary differential equation if the function f that I've described over there is linear in y and its derivatives. Well, thank you before I erase. This is a linear second order differential equation. X doesn't matter as far as linearity is concerned, so it's just a question of whether it's linear in y and y prime, and they don't even appear, so certainly it's linear. In other words, we can write this in the form, let's see. In our case, a and b are equal to 0 for this particular example. And that's what makes it linear. So it's a linear expression in the variables y, y prime, y double prime. Although actually we could even allow coefficients that involve x, and it's still considered linear. Let me give you some additional examples. This one, however, is not linear. Maybe before I erase. This is not linear in y prime because it's being squared. is linear. We're viewing this as a coefficient. So it only has to be linear in the variables y, y prime, and so on. So this is second order linear. But as soon as I start putting powers in there on the y's and y primes, or if I maybe do something like, let's just change this a little bit. No longer linear. Still second order, but it's not linear. Let's see. Could leave the left-hand side on this alone, or leave the right-hand side alone. That's no longer linear. Oh, whoops. Okay. That's no longer linear. So this is what about y? Linear. Oh. Who thinks it's linear? Thinks it's not. It's not linear. For the same kind of reason that, by the way, if you were looking at a function of the variables s and t, that's not a linear function in s and t. A linear function in s and t would have the form h. Have some form like that. But as soon as you start multiplying s and t together, it's no longer linear in s and t. Well, as you maybe could guess, if differential equations are not linear, they're generally much harder to solve. Linear equations, we typically will develop some techniques for solving them, although if you start making coefficients non-constant, they get a little tricky. But if they're constant variable, constant coefficients, and especially if you have 0 on the right-hand side, those are pretty easy. You may have even encountered those in the calculus class. But non-constant coefficients, the right-hand side is not 0. We refer to those as non-homogeneous, by the way, and we'll see those later. They get a little trickier. Any questions so far? Well, you'll have lots of practice and homework doing some classifying. Let's go on and talk a little bit about solutions. Solution of an nth order differential equation. Ordinary. Unless I say otherwise, they're ordinary. As you'll discover, it's hard to separate intervals when you're talking intervals from the notion of solution. So whenever you're talking about a solution, you usually are going to be also saying something about the interval over which it is a solution. theta defined and n times continuously differentiable on I. So obviously the solution function theta has to be defined on I, and it has to be n times differentiable, and those derivatives have to be continuous. It's a pretty strong requirement, but that's what we do require. Well, this is maybe a duh statement. It has to satisfy the equation, but what exactly does that mean? It means when you take the derivatives of theta with respect to the independent variable, plug those all into the equation, it makes the equation true. It's like an algebraic equation. Well, until we get to some specific techniques, we'll just concentrate our efforts for the time being on verifying that a solution, that we have a solution. In some cases, there are some obvious techniques, like the example we looked at earlier, where integration was sufficient, or perhaps where just by inspection you could tell what a solution was. But most of the time, it's not quite that obvious. So here's a differential equation. Let's classify it. Order is obvious. Second order. Obviously an ODE. Linear? Non-linear? Linear? Yeah, it's linear. And I'm just going to claim that function is a solution on this interval. I'm not saying it's the only solution, I'm saying it's a solution. That's my claim. And to verify that, it's just a matter of computing the first and second derivatives of that function. Make sure that that the second derivative simplifies to e to the 2x. So that's easy enough to check. Provided you take derivatives of exponentials, which hopefully will. First derivative is 1/2 e to the 2x. And the second derivative is as required e to the 2x. And that's all that's necessary to verify that it is a solution. And it's a function that's defined from negative infinity to infinity. And there's no reason to expect that this isn't a solution on that entire interval. That function. By the way, this is one where maybe you could have come up with a solution without too much effort, right? Just by integrating it a couple times. Choosing your constant to be 0 every time. Here's maybe one where you could maybe just by inspection come up with a solution. We're looking for a function y such that when you add the function to its second derivative, you get 0. So I guess in other words, the second derivative should be the opposite of the function for all values of the independent variable. Anyone want to take a guess?
Cosine.
Sine or cosine, actually. Yeah, let's just put one. Equals sine of t. And again, this is going to be the solution on a set of all real numbers. To verify that, the first and second derivative. Well, actually, you only need the second derivative, right? But you have to get to it through the first derivative. And then if you add y to the second derivative, well, you get 0 for all t. So to claim that this is a solution, it has to satisfy the equation for all values of the independent variable in this interval. That's where the interval comes into play. And it certainly does. Because this is true for all t. let's classify first. Yes, third order. So don't be misled by this. The order is determined by the derivative. Oops, sorry. It wouldn't be correct without that, would it? Leaves notation. So without that, I'm not sure what it is. It's just nonsense. So the third order, is it linear? No. Because of this term. So it's third order, nonlinear, but it is an ODE, of course. And I claim that it's that a solution is that. And again, on all the numbers. Let's just check that real quick. We need to have information about the third derivative. Oh, wait, yeah, where does the 36 come from? That's the problem. How about 24? Some new calculus will that'll work better. Okay, so the third derivative. And by the way, if you're more comfortable with prime notation, then leave this. Most of the time, you can just kind of go back and forth. The disadvantage of the prime notation, though, is here it's not clear what the independent variable is, whereas it's very clear here. So that's one advantage you get in this notation. So, third derivative plus the fourth power of the first derivative simplifies to 14 plus 4 to the fourth, that better be 256. Got one error here. So that's what the left-hand side simplifies to. And the right-hand side, sometimes it's beneficial to work with each side separately. That's what I'm doing here. So it's 256 times x to the fourth cubed plus 24. And of course that does simplify to the same thing. So it is a solution. Okay, so far. Oh, just one last example, maybe to say a little bit more about this whole issue of intervals. Here's one where maybe you can come up with a solution. What? Natural log. Just integrate this into 1 over x in natural log. Absolute value of x. Generally speaking, we want to find the largest interval possible over which the function is a solution, and we want to avoid, generally speaking, discontinuities. And so, normally, even though this function has its domain, all reals except 0, we would specify one interval or the other. We want an interval over which this function is a solution. It's not a solution over all real numbers. Technically speaking, the interval from -infinity to infinity with 0 excluded is not an interval. But on either of these two intervals, this is a solution. So there's a distinction made between the domain of the function and the interval over which it's a solution of a differential equation. So occasionally you'll have to be able to make that distinction. Most of the time, it's not going to matter too much. It's not going to be an issue, like in the previous examples, but it does occasionally pop up. Yes?
Okay. So the range is between the value infinity to 0, so which
Yes, because that's especially why we want the absolute value, is because there might be instances. So for example, if I said, let's see, well, it jumps ahead just a little bit, but suppose I wanted the solution for which this was true and y of y of negative 1 equals. No, not that. What do I want? 0. Well, if we leave off the absolute values, there's no way that we're going to get a solution that satisfies this property, because without the absolute values there, I can't plug negative 1 in for x. But yet this still is a function with the absolute values there that satisfies this differential equation. You take the derivative of the log of the absolute value of x, you still get 1 over x. But if this was my stipulation, then the solution would be this over this interval, as opposed to this interval. Because I'd have to have an interval where negative 1 was an element. It's certainly not an element of that interval. So this would be the interval of solution. This would be the function. The solution of the differential equation over this interval, or this differential equation. This is what's called an initial condition. We'll talk about that. Let's see if that's coming up in this section. Yeah, it's coming up shortly. I'll leave it go for just a little bit longer before I give a formal definition. But this is what we call an initial condition. It defines what's called a particular solution of a differential equation. Any other questions before I go on? Okay, another type of solution, these are all examples of explicitly defined functions. In calculus, you may recall the distinction between explicit functions and implicit functions. Does that ring a bell? Well, all of the examples I've done so far have had solutions that are explicit, in the sense that we can explicitly define the dependent variable in terms of the independent variable. But not all functions are defined, can be defined explicitly. Let's give you an example. Well, let me first say what is meant by an implicit solution. It's a relation of involving x and y, so an equation involving x and y. That defines at least one solution of the standard kind of form, theta of x, that satisfies both the differential equation and the relation. Understood here that y is the dependent variable and x is the independent. So this is our differential equation. It's still first order. Let's see. Would you consider it linear? No. Even when you put it in a form, necessary form, if you multiply through by this, you're going to have a product of the derivative of y times y involved. That makes it nonlinear. Well, here is a solution. function involving x and y that I claim satisfies this differential equation. And I also claim that it defines at least one, and actually two, functions that could be written in this form, or standard explicit form. Let's first verify that it's a solution. Remember how to do implicit differentiation? Does that ring a bell? It's a technique that's useful for finding the derivative in cases where you can't rewrite this in explicit form. Should I do that real quickly maybe? So what you do is you take derivatives on both sides with respect to x. So all derivatives are with respect to x. Y is understood to be the dependent variable. In cases like this, you just use the normal rules for differentiation. The derivative of x squared is 2x. But here, we've got x times a function involving x. So we're thinking of y as representing a function in x. So what do we have to do to get this derivative? Product rule. Yeah. So we take the first times the derivative of the second. But the derivative of y is just dy dx. Plus the second times the derivative of the first with respect to x, which is 1. So all derivatives are with respect to x. So this is the product rule. This, well, we have to take the derivative of y squared with respect to x. That requires a chain rule. So this is just 2y times the derivative of y. The derivative of the outer function times the derivative of the inner function. Chain rule. And on the right, we get 0. And now all we have to do is collect all the dy dx's together, solve for that. And it's not too hard to see that it leads to this. So if you leave the dy dx's on the left, subtract these terms to the right. Actually, let's a couple steps at once here. So this and this both have dy dx as a factor. So let's factor that out. Take this term and this term to the right. Divide through by this factor. Get lo and behold. Curious, I really worked backwards on this to come up with the example. I started with this, used implicit differentiation to find the derivative, and then wrote out the differential equation. It would be very hard to start with this and come up with this as a solution. That would be very difficult. But it's easy to verify. And it is a solution, it's an explicit solution, implicit solution, in a sense that, well, first of all, we wouldn't want to solve this for y, but you could. In this particular case, sometimes you can't, but in this case we could actually solve this for y, just using the quadratic formula. And you'd end up with two solutions. Let me just write them out. You don't have to, in fact, we will normally not even go this far. I just want to at least once mention that if we chose to on this one, by the quadratic formula, treating x and x squared like constants. Solve for y, get two solutions. You can kind of see the quadratic formula showing up there. So we're producing two functions of this form, both of which satisfy this differential equation, and both of which would satisfy this. In other words, if I plug this in for y here and here and simplify, I get 7. You wouldn't really want to do that, but you could. So it satisfies both the differential equation and the relation. And this one does as well. But normally what we'll do is, if instances like this arise, where we're able to produce a solution that's expressed implicitly, unless it's real easy to get an explicit solution, we'll just leave it in this form. And understand that this does define two or more solution functions. Okay. We'll take a break shortly, but let me, I think we're almost finished with section 1. Let me wrap up section 1, then we'll take a break. I mentioned the term particular solution, and that's as opposed to general solutions. Typically, when you solve a differential equation, you produce a whole family of solutions that involve one or more parameters. Here are two examples. Again, don't worry too much about how these are found, although this is one where you can pretty easily, in fact, we did this one earlier. I think I was just using y's and x's instead of x's and t's. This one we have written down one solution before, but it turns out there are many others. All of which have that form. C1 sine of t plus C2 cosine of t. So in this first example, I'm getting a family of solutions with one parameter. This is what we call the one parameter family of solutions, surprisingly. Here I get a two parameter family of solutions. No matter what I plug in for C1 and C2, the function that resolves will satisfy this differential equation. And you can verify that, by the way, by cranking out the first and second derivatives, leaving the these unspecified constants in place. And you see that it still simplifies to 0 on the left-hand side. So these are what we would call general solutions of the differential equations. But there are times when we're interested in particular solutions, as opposed to this whole family. And particular solutions are determined by some additional criteria, sometimes called initial conditions. So for example, if I wanted a particular solution that satisfied this equation, and also the initial condition where x of 0 had to be equal to 1, well, this would still be my starting point. But now I want to choose a particular c so that when I plug 0 in for t, I get 1 for x. Well, when you plug 0 in for t here, oops, sorry, not 0 there, c there, you just get c. So in order for x of 0 to be 1, c has to be 1. So the particular solution looks like that. So it's a function that satisfies both the differential equation and this condition. Graphically, general solutions are families of graphs. So if you take 1/13 cubed and add c to it, you get graphs that look like this, depending on what your, oops, sloppy here, depending on what the c value is. The c value would determine the intercept. So this would be a graphic representation of the general solution. The particular solution is the one that passes through point 0, 1. So this is the x-axis, this is the t-axis. That might be that, let's say. So this is the particular solution. So one graph out of the whole family is what represents your particular solution. Same kinds of things can be done here, just with a little bit more effort. You'd have to have, in this case, 2 additional conditions specified to determine both of these constant values to produce a particular solution. And then one last thing. Unless you have questions, maybe skip over something that you're not sure about. Along with the term particular solution, there's also what's called a singular solution. Particular solutions are ones that can be obtained from the family of solutions by choosing a particular constant. Singular solutions are solutions that also satisfy the differential equation but can't be obtained from the parameter solution, the general solution. Well, I'll leave this for you to verify if you're interested. This happens to be a one parameter family of solutions that satisfies this differential equation. Compute the first derivative of this, show that that first derivative is the same as taking x times the square of this. It's a little bit of work, but you can do that. However, there's one more solution that, in addition to all of these, that you can obtain by choosing a particular value of c. It's one that maybe you can recognize. Can you think of a function of the form y equals something that's going to satisfy both this side and this side? It's simple. What? Zero. See, this is a function, right? Horizontal line passing through the origin. And it satisfies this differential equation. You take the derivative of y equals 0, you get 0. You plug 0 in here, you get 0. But it's not a solution that you can get by choosing a particular value of c. There's no value of c that's going to give you the constant 0 function. So this is what we call a singular solution. That's what we mean by singular. Maybe just one more example. This is kind of similar to this, but there's one that we're going to use over there. So here's a one parameter family of solutions that you can find using some of the techniques that we'll be studying. But just like this one, there's another solution that can't be found using any given c. That's y equals 0 again. Now, not all singular solutions are y equals 0, but in this particular pair of examples, it is. Yes?
So why did you say y equals 0?
Oh, because just like up here, if you take the derivative of y equals 0, you get 0, and if you plug y equals 0 in here, you get 0. So this also satisfies this differential equation, in the sense that its derivative and the function itself, when plugged into the equation, makes it true. So if the derivative is 0, and we plug it in there, you get 0 as well. So it satisfies the differential equation. So these all satisfy the differential equation, but this one does as well. And this one can't be found by just letting c be some specific constant. All right, anything else? Okay, well, that's the end of section 1. Let's take a 4 or 5 minute break, reconvene, start section